So Nils, thank you for being here, and the button is yours.
Thank you very much, Areti. Yeah, I think that's a good introduction because I'm just looking at the previous speakers somewhere in the middle between all the experiments that enable architecture and then the industry that is kind of bothered with delivering what we think up. And when we set out our research group about 8-9 years ago, we've been a much smaller office and I kind of grew with it. So nowadays, my biggest concern is really to get big projects built, and I'm almost kind of moving to the client side of our own research group, trying to get solutions for real-world problems. And I believe we are at a very, very interesting point in time when it comes to applying everything that we see here on this great conference and that we find in research technology to real-world projects, because we have a couple of trends that have been kind of becoming emergent in the past decades that kind of started as separate but correlated processes that start to converge now and start to suddenly generate solutions at a scale that we couldn't fathom 10 years ago. So I think the first one, which is not really tangible in terms of production, but just really made a huge difference for us over the past 10 years, was integrated design and delivery. That essentially means that we kind of move away from stage gateways and from separation of design, procurement, and construction, and start to completely integrate these processes and really get hands-on with manufacturing, but also at large scale using technology that enables us to work with really big data sets. And the second aspect is market-ready digital fabrication, because when you go beyond experimentation, there's also an element of feasibility, which is quite a pressing factor in architecture, because architecture is not really an art form, it is about building stuff, and if you want to build stuff, no matter what it is, it has to be feasible. And we're now at a point where a lot of tools that have been feasible in other industries now finally become feasible in the construction field. And now we also see, and this is what this conference is mostly about, is how prototyping technologies become available at production scale level, starting with small projects now successively moving into larger ones. So there's a massive potential also in scaling these approaches up. And then we have another very interesting tendency, which is having multi-property material mixes combined to give you completely new abilities, which means you can go beyond adding components. You can actually have components adapt to local conditions. So these are all things that are kind of happening at the moment, and they also seem to accelerate somehow in coming together. But maybe starting with kind of where architecture is nowadays. This is clearly not a building, but it's quite relevant to really where we are with kind of big projects at the moment, is kind of comparing a bit to what happened in the aviation industry over the past 40 years. So this is an image taken on the 30th of September 1968, rollout of the first 747 in Everett near Seattle. Everett was really that hole in the ground. It's now the biggest building in the world where these planes are still manufactured. They look very similar, but they changed drastically. And it's very similar to the change that we went through in construction, only that in construction it happened a bit later, maybe in the past 15 years. Started with Frank Gehry kind of introducing this kind of computational environment into construction. So this is how a plane is conceived nowadays. It's pretty much pre-simulated, pre-assembled. We know what it is before it flies. We can actually test it before it flies. And using pretty much the same software, we do the same with buildings nowadays. That means we get much better predictability. We can work on tolerances. We can make our buildings more efficient. But also it means we can much easier integrate results from other disciplines and make our results and our studies and our concepts more relevant. Another trend that you see in aviation, comparing the first 747 hand-assembled from 3 million individually made parts, and this is a 787, down to 100,000 pre-assembled composite elements. Massive change, an order of magnitude change in the number of elements. There's also a trend in construction industry that you kind of start to decentralize complex assemblies, bring them in as subsystems, and assemble them on site. So if you look at a building we recently developed, also one of the very early strategies is we kind of take this building apart, spread it out over the industry, have different manufacturers coming together and kind of in parallel producing these tasks rather than bringing everything in sequentially and piling it up on site. And then also comes a very important factor in the everyday work, and this is also where digital tools play an enormously important role, is that you start to decentralize not only the production, but also the engineering. So rather than having a centralized office where everything happens, you start to decentralize knowledge and engineering globally. And this is also why it kind of, probably also the reason why we're in London really, because it's a very kind of international hub. We have 55 languages spoken in our office because the production end of construction is still a very local trade. So you have to really look at each market, you have to be able to communicate, find out what is possible, and then feed it back into the design team that they can work with local expertise and ingest it at very early stage. And the sooner we can bring this production knowledge into our projects, the more relevant they become. Relevance or performance can have many dimensions. It can be feasibility, cost, speed, also the amount of time that we as designers can then invest into the project to make it the next exciting thing. And then, of course, it all has to come together on site. In the aviation industry, you have a lot of kind of very interesting devices for that. In the construction industry, we now really start to ship things globally. You have a theater in Reykjavik in Iceland with a facade made by Yuanda in Shanghai, shipped on a container boat, and actually could feasibly do that because they were so much more efficient in production that they could offset the transportation disadvantage. And what then comes together in this largest building in the world is kind of what happens on construction site these days, where you have just-in-time delivery from production facilities all around the world, making sure that stuff exactly arrives when you need it, because in dense urban agglomerations you are kind of very limited with what you can do in space in terms of arrangement on site. So these are kind of things, I won't bore you with the details of that, but there's a lot of kind of similarity, starting a bit later in architecture between the aviation industry and architecture, getting us to kind of where we nowadays, where we have really decentralized engineering, concurrent engineering, which means rather than having design first, then comes an engineer, changes it a bit, and then comes a shop drawing planner, we really start to kind of have these things happening in parallel, and it gives us more relevant results. And looking at this building, this was kind of, sorry, I'm getting confused here, a milestone for us where we could compress or see the advantages of kind of these separate stages that you find in construction. Again, this is very specific to how to put an architectural project together, but really to really just go into two integrated phases, which means there's one big design phase that goes all the way, there's actually an overlap here, into shop planning, and then you get very smoothly integrated into the delivery phase. And I think if contractual models develop as quick as technology does, we will be even able to break this boundary and have direct feedback loops from production into the design model. That's kind of where the similarities end between aviation and architecture, because architecture deals with a very specific problem. Every building is kind of a prototype in itself, which means all the research and development you need to do exactly one time. It's very hard to recycle processes. We're also working on that with parametric design, so we actually, rather than do sequential notations, we create topologies or information networks that can be reused across projects. But if you look at the development budget of a building, even if it's a very big building, if you're lucky, the entire design team, and that includes shop drawing production, 2-digit millions. So let's say 20 million pounds on a large high-rise building, entire design team. If you compare that to what you have in automotive, it's about 2 billion pounds to develop a car. Yeah? And I mean, that's kind of the technology we're trying to learn from. But I think what this is saying is that the efficiency of these systems has to reach a certain level before they can actually trickle down into the construction industry, because the amount of resource you can develop into research and development is by several orders of magnitude lower. And then when you look at my initial example, aviation, wrong button, that's about 20 billion per design in pounds, about kind of 28 million, a billion euros to develop an airplane. So yes, we are very ambitious when ingesting this technology, but when I talk about convergence, one of the very interesting points we had is that there's a lot of technology that is out there, ready proved, now suddenly becomes feasible in the context of construction. So very interesting point in time. And actually enable us, and this is a photo, not a rendering, to do buildings that 10 years ago, yes, you could have designed them, but you couldn't necessarily have built them. And we are now really at a point where we see the benefits of this technology, and the work that started 10, 15 years ago when architects started to explore digital fabrication really come together in the real world. So it's a really interesting point. So we can afford more complexity in our design because we can feasibly manufacture it. Kind of an incredible amount of similar but really different parts of manufacture done very efficiently. We get better performing projects because we integrate more knowledge at an earlier stage. And this is where the process is important, the concurrent engineering aspect, allowing us to work in parallel with guys, for example, acoustic engineers, fabricators, reducing tolerances, getting better performance within the built environment. And at the end of the day, we also, as designers, can, yes, there's a pressure on getting tangible results sooner, but also we can stretch out this process longer. So, and also we can have more information and more inputs that we can use. So I believe we can also do better designs in these environments, because at the end of the day, it's not an isolated task. I think design really ends when it's built. And a very important side effect, we become faster in architecture. For architects, big advantages. We can build more buildings in a lifetime. You can't imagine, I mean, like 20 years ago, you had maybe 5 buildings as an architect, big ones, and that's it, show over. And it also has the advantage that we can actually, as architects, can cater for a bigger part of the industry. Only 15% of buildings around the world are actually designed by architects. The rest is kind of generic, kind of industrial production architecture. So faster delivery means also we can scale out the effort a bit bigger. I want to show you an example about where we currently are at large scale architecture. This is a project we did in China in 2010. It was a milestone because first commercial project in a fast-paced market. So in 2010, the architecture market in China was booming. And about a third of the budget that we had in Europe, the ambition was to deliver to a standard that was globally recognizable. We introduced some ideas that are not necessarily common in commercial offices, like we want to get a lot of daylight and also wanted to create a very pleasant environment. So huge ambition. Yes, we architects can always come up with nice design models, and then just going through kind of what the process nowadays is. The first thing you need to do is to rationalize it, because you want to A, distribute it, and B, you want to make it feasible. So you can't really build any shape yet. Once you're kind of rationalized, you can actually start to spread it out to decentralized engineering. So all the facade engineering and structural engineering was done in China, whilst we are still kind of heavily taking along. And then very quickly, you need to get your hands dirty and actually go to the workshops and find out how does the material perform. And I think that's also kind of a bit where Ferran is, that it's still manufacturing, right? So it's not that you can just completely kind of digitalize manufacturing. You need to understand how the material behaves and what technology they use. And there are very different approaches. So some guys will dangle everything by hand with incredible precision. Others would kind of invent very ambitious kind of automated stamp processes, but they compete in the market, and sometimes that is what you get, and you have to make it work. But the great thing is we can now, while you test it, you look at contractors' proposals, because again, there's a lot of delivery knowledge that you don't necessarily have as a designer. But as we now break down the boundaries between these steps, we can actually get hands-on production knowledge and improve our design model. And then re-ingesting these things that we find in the experimental process back in the live design, this is really key. And again, every building is a one-off prototype, so this shortcut is essentially giving us now already quite an improved design quality on site. Here, sometimes you ingest something, an engineer heavily walks off, someone builds a million, and then lucky enough you find out actually before you hit the construction site that stuff doesn't fit, so we can work around it, redesign, re-engineer. So we are now, I mean, this is really the stage that the kind of aviation industry is at the moment. With current technology, we get a lot of pre-visibility. We get cheaper because fixing that on a computer is several orders of magnitude cheaper than fixing on site. And in a normal project, you budget about 15% of your construction budget for problems like these, because normally you find out too late and then you have stuff happening basically. But then again, we can actually look at what has been built. We can scan the results and we can re-inform the next level of production. So this is really when you start to shortcut manufacturing and design, we can actually on the fly make adjustments to something that is just under production. Problem here is tolerance is maybe 10 centimeters. Facade, you get down to millimeters. So if you know what's going on here, you can make adjustments to stuff that is still kind of under manufacturing, and it simply means you can put these things together much quicker. That's a concrete frame scan model. Facade fits then on the real world because we know what it is, and we can make adjustments to stuff that is still in the workshop. Here you see a facade assembly line. This is for a different project I will briefly show later. These panels are not rectangular. They're actually all different. They're working with certain tolerances that you can do by cold deforming them. And it's a project with 12,000 trapezoidal window panels. And we do spot checks in the factory. You see this one has a 92.69 degree edge angle, and we pretty much match that in the factory. And this is because we can directly feed our 3D design models into the manufacturer's production line, kind of ingesting the data or actually generating the data that they use to drive the machine. So we also cut out the middleman in terms of shop drawing to reduce sources of error and to reduce unnecessary loss in information. Very important aspect as well is instructing guys on site. So we brief foremen that then go on and deliver this. And what we then, in the end of the day, get is a building that is, this is not a public building, not a cultural building. This is a commercial building. It's competing in the market. But through this increase in efficiency, we actually get qualities introduced that give them, our clients, an edge over the competition, that actually contribute to a better built environment, because we can very feasibly all of a sudden do kind of very delicate structures, get a lot of daylight in, do nice cladding to it. So yeah, kind of gives us happy users of the building. Most importantly, gives us a happy client. This is probably currently the most successful businesswoman in the world, Zhang Xin, one of our clients. And she's so happy because we actually got very, very fast in delivering her building. So this was the first one that I've shown. The next project, you see construction time kind of stays the same, but through integrated design and kind of sharpening our process and getting used to working with collaborators, we are able in the third building to almost halve the design time. And we didn't get less ambitious, so that's the next building. Very little similarity, kind of a lot of firsts in construction. Built. This is also not a rendering, this is actually a photo of the third building we did. So we're not necessarily bending down our ambition. We use the time we gain actually to then focus on new challenges in design. So quite an interesting journey. This is the fourth one we do now for her. Tallest atrium that has ever been built on a similar timeline. So we actually pick a new challenge for this one because we were able to reuse a lot of the processes that we have developed for other buildings and can now actually focus on the next task. So kind of enables us, it buys us more time to kind of push the envelope a little. So this one is going about 8th floor now, right now under construction. And this is a very interesting, it's kind of the accumulation of this tendency. So very ambitious building, 315 meters tall, highly seismic zone. Works with a perspectively enhanced effect, so the building is 12 meters narrower on the top than it is at the bottom, but we don't want to create singularities in the envelope, and this is where all the trapezoidal glass panels come in. So these lines just kind of nicely create an enhanced perspective effect. We have 12,000 different glass panels, more than 10,000 different fiber concrete panels, and we built this thing from design, start of design, to finish of the shell in 2 years and 10 months. And we still have to verify that, but our engineers claim that this is the world construction speed record in high-rise buildings, and actually we didn't have to trade in design ambition to get there. So this, funny enough, only covers the first 2 points that I've been mentioning, integrated design and delivery and market-ready digital manufacturing. So what about the other 2 things, which are kind of where we are going now with the development? That's prototyping technologies and emergence of multi-property composites. I drew this graph on the plane. It's a bit rough, but I think it kind of tells the story where we are at the moment. So if you look at performance in design and construction and complexity, you have the standardization, which is kind of going from a clay hut to a brick. Here gives you kind of efficiency benefits. I think where we are right now is rationalization. Then you go to mass customization, where you can actually truly customize each and every panel. Then you get into panels that can locally adapt to conditions. And then at the end of the day, you have a component that is actually able to actively adapt, which is kind of the ultimate goal. And it's kind of an evolution from a brick to a organic cell, really. If you look about where we are, and I think right now, really, with large-scale projects, we are about here. So there's a lot that we can still do. So we are now able, through smart rationalization and through good processes, to do designs that weren't possible 10 years ago. Quite interesting, though, last month I found out that I'm wrong. So this is taken in a workshop of a contractor that I visited to inspect a mock-up, and I said, okay, that's a pretty new robot, what are you doing with it? And I said, yeah, I'm doing my formworks with it. And I just ordered the second one, and actually, I will be doing your entire building, custom milled. So this is a project we're doing in Northern Africa, a theater for Morocco. Oh, I have a second screen here, that's very convenient. And it consists of 3,300 fiber concrete panels. And as in every project, to be able to get away with this kind of shape, we have to pre-rationalize it. So a lot of our energy in very early conceptual stages, when you compete with others, is to explain that this is buildable. And we need to do that because whenever you do something that is non-standard, you need to deliver proof of concept. Otherwise, people say, nice design, but sorry, doesn't fly. A lot of our tools kind of currently deal with these problems of early stage design rationalization. And project currently looks like this. So the delicate kind of concrete goes up, delicate parts aren't on there yet. So this is kind of how these facade panels look like. We looked at the mock-ups, and this is one of the curved parts we always tested. But actually, he now tells me that he will treat, regardless of whether it's a flat panel or twisted panel, single curvature or double curvature, he will treat them all the same because it's more efficient, which means the price point of using CNC technology is now at a level where you don't have to rationalize anymore. And this is just something that I found out by coincidence last month because he already won the job. He had the rationalized technology, but as a competitive player in the market, he chose not to work with the rationalized geometry, but to actually use a CNC manufactured process throughout, because apparently the technology is now ready for the market. And that means we don't need to do this anymore. We don't need to do any of that, and we don't need to do any of that, and we also don't need to do any of that anymore, which means we can now focus on surfaces that actually can be more relevant in terms of geometry, because we don't need to compromise for CNC production anymore. This is now a sub-assembly of a building. It's a facade, but it's probably the most costly one. So on a high-rise building, depending on fancy you want to make it, 40 to 60% of your budget goes into what is the facade of the building. So I think it's kind of the most important sub-assembly of a building. So we kind of now, very silently, and I just found this out by chance, move into mass customization, and I'm almost done coming to the conclusion, because where do we go beyond mass customization? We are very intrigued in our research group, and this is now getting a bit back to the front end, to the experimental stuff, into efficiency, kind of efficiency of systems, because it also has an aesthetic dimension. We very much like natural structures, and we find that if you make things more efficient, they usually also start to look very interesting. So this started as an aesthetic experiment, but we work a lot with, and which is very similar to projects presented earlier on, like self-supporting thin shell structures, form efficient things. And we are now at a level where we introduce them in construction projects. So these are images taken from a project which is now in construction documentation. So it's a real project where we do a thin shell concrete shells with integrated properties. Lighting is embedded. The positions of the roof lights is actually not to collide with force flow in the shell. So we take a material away where we can take it. We add other properties, but unfortunately still a very conventional process. So this will be standard in form making and then just a massive concrete pour. So advanced in form, not really in production methodology. And that's now where the next step in evolution comes, is where we can actually use prototyping technology to create products that only apply material where necessary in a smarter way. So this is kind of a test job that we run in our research unit, where we basically started off with a piece of furniture that we can also rapid prototype scale-wise. Looked at the convergence of force flow, kind of the aesthetic element and the aspect, and designed a chair that is actually very reduced in material usage. Basically, you have to sit vertically on the prototype because it doesn't really deal with kind of too many load scenarios yet, but we're getting there and we're prototyping that at the moment. So you see how we can then use kind of the ideas we have in large-scale architecture and already kind of get them on a product level at very small scale. And the other interesting aspect of this is that we can now also get hybrid materials. It's not a true kind of high-performance composites because it's still kind of the same base material, but through changing additives, we can now control the softness. It's a bit what's happening in modern trainers. So we can actually have soft zones where you kind of sit, stiffer zones where you kind of rest your hands. So we can actually start to control and material properties. And this actually will be productized now. So we hope that we get this to a shop near you at some point, which is kind of a step for us because it's now something that starts at small scale that has a huge potential for large-scale projects. So we now get actually from mass customization to adaptation of materials to address local conditions. And the next step really, which is adaptivity, is where the true potential lies. So, by the way, adaptation also means that we can now do what we have done at prototype scale 10 years ago for pavilions, kind of completely 3D-formed surfaces now, technically at a industrial scale, more feasible. But the true kind of goal is to get to adaptivity. And this is my second to last slide. Section through a human collarbone, not mine. Mine would look different. And the amazing thing here is that these organic systems are able to not only very efficiently encoded kind of distribute material, it also shifts, which means over 10 years, if I change my usage pattern, my bone density changes. It's already a problem for long-term space travel. Like if you are on the ISS for 180 days, your bone structure looks different because it just gets rid of the energy that your body needs to carry it around, and it basically allows you to afford a more luxurious brains than other animals who don't possess these abilities. And if you think about how quickly we went through these steps in the past years, bringing production or advanced production into construction, there is a massive impact that this can have when you are able to scale it out to large-scale applications in concrete. So picture this being a piece of engineered concrete and roll this out in growing economies such as China and India, combined the biggest bunch of people in the world. India has a urbanization of about 36%, China currently 53%, both aim at getting to about 85%. 300 cities in China with more than 1 million inhabitants, so we more or less will be looking at doubling that to a certain extent to meet with urbanization goals. So these efficiencies, so imagine you can buildings, and it's realistic, we can simulate this, we can build buildings at a third of the weight that we currently have, so which means we can get a completely different way of using materials efficiency. And I believe that this day is not too far away, looking at how these things come together at the moment. So I think if the Moore law now also starts to apply to the construction industry, we will see that happening very soon. Thank you very much.